And so let me do a little demonstration of this cool thing I made a few years ago. It lets you run SQL within an IPython or a Jupyter notebook. Look, it's SQL results, and that's so cool. I love it. And all you had to do to connect was put in the SQL Alchemy connection URL up there. And in fact, you can capture it in a variable, and you can inspect the rows. That's really cool. Okay, so I made this demo, and now I want to commit it, of course, and I want to push it up to, wait a minute, what happened? Cannot proceed. It wouldn't let me commit. Why wouldn't it let me commit? Well, I'm trying to commit something that has a password in it, which is not a good idea. And in this case, it's just a password to a throwaway local database. When you do this to something that's real, then your life immediately becomes hell, because now this password is out there in the wild. You need to change the password. You need to try to get it out of the repo. You need to look through logs to figure it out if anybody grabbed it during that time and accessed it. It's horrible. So obviously, A, never commit anything that has a password. No, but of course, you shouldn't rely on your human fallible instincts like that. So B, put it in your .gitignore if you know that it has a password. But again, that's relying on you knowing, being alert enough, thinking, okay, I'm putting a password in this file. I'll put it in my Gitignore so that I don't accidentally commit it. So that's what Git-seekret is for, and which is the script that basically put in a Git hook that stopped me from committing this file. So Git-seekret was not invented by 18F, but I think that we did a pretty good job of writing a nice install script and adding some rules to it. So I suggest using our fork, because this is a security mini-conference. I'm sure you'll all be totally happy to curl something right off the internet and pipe it through bash, right? Fine, be that way. We can go ahead, inspect it, whatever, load it locally. But the point is that we do have an installer for this. And what this basically does, I don't need to clone that. We have a set of rules, and a single rule. In this case, I'm not sure what all you can do with these rules, but in this case, it's just a regular expression that was to try to recognize a SQL Alchemy database URL that includes a password and exclude it. So yes, if you install Git-seekrets, then you write your own rules for the kinds of things that you do not want to leak into the world. Several of these rules, I think everything except dbURL, already comes with the 18F version of Git-seekret. I'm going to try to check this one in, the dbURL one in, over the next few days. I'd love suggestions for other ways to catch database passwords, because that's the sort of thing I worry about. And the other cool thing, if you look in, this is all within the 18F laptop script. If you want a duplicate of the 18F operating environment, that script is open source too. Go for it. That's for Mac only. Sorry about that. But Git-seekret should work in Mac or Linux, and including this installer. And I'm not going to get into this. I will put this notebook. I'll make sure that Calvin gets it so that I won't get into the details, but there's a little test framework to test out your rules, make sure those work, add the rules to the installer. So yeah, stop leaking stuff onto GitHub. Sharing is wonderful, openness is wonderful, it can go too far. All right, I'm done.
Hello everyone. So when Colleen asked for lightning talks, I thought, well, Python and security, I couldn't really think of anything that combines both right off the bat. So I thought, well, I'll do something on security, in particular something that's been in the news a lot, namely the Spectre and Meltdown. I'm sure everybody heard of that. And so, and I like to make it challenging and actually do some live demos. So we'll see here. So what are cache tabbing side channel attacks? Modern CPUs very heavily rely on a hierarchy of caches, as I'm sure many of you know, and accessing memory that's in the cache is much, much faster. It's orders of magnitude faster than if it's in main memory. And we can actually measure that relatively easily, even from user mode, and use that to determine the execution times of algorithms and clean information about access patterns. So I'm gonna start out with that. So here we enter presentation mode, And this is in C++, not in and assembly, not in Python, I'm sorry. So this is kind of to warm up a little. One of the challenges, okay, how do we measure the access time? And this is a little bit of assembly that actually measures how many CPU cycles does it take to read a byte from a particular memory address. And actually on an Intel CPU, it's from a cache line, which is 64 bytes. And all the rest here is trickery to make sure that the pipeline, the microcode pipeline is flushed and we just measure exactly what just the instruction ticks. So what we do here, we allocate some memory, and then we use a special instruction to flush all the memory into all the caches into main memory so that we can show how we read from cold. Then we measure how long it takes for the first access and then for the second one. So here we have a cold access time, and I'll flush it again, and here I'll show, okay, I do an actual read, then I measure it again, and then do another cold one. So we will do a cold read, a warm read, and another cold read. So, oh, I can't believe that. Where did I mistype here? Oh, here we go. Okay, can you see this? So the cold access time, the first time it takes 215 CPU cycles, the second time it takes 25. So an order of magnitude faster once it's actually in the cache. If we read it, again, here I show that, well, the first one is here equally fast because we already primed it by doing this read here. So this is kind of like setting the stage a little. So now what happens gets more subtle. With the Spectre attack that you specifically heard and also Meltdown, because of, again, all the operations tend to be very expensive, and so being able to do branching in code means if you get it wrong, then you have to load additional code and decode it, and so your microcode pipeline will potentially stall. So modern CPUs have very sophisticated branch predictors. So it speculatively executes a branch that it thinks is right, and then if it turns out to be wrong, it discards the result. But we can actually see the fact that it read past the branch. So I'll show that here. So basically what I do is do the equivalent to this. Basically, let's assume we have an array of memory, and we know the bounds of it, how big it is. So we do a check. Is my position where I want to read beyond that or within the bounds? If yes, I return the value, I read it and return it. Otherwise, I return 0 in this case. And so this is basically the equivalent in assembly, so I can be sure that I know what is being executed. So let me turn this on. And so what we do here in this code is I first do a quick loop where I read in bounds. So this is my memory bounds, and this is my access point where I read from. So I read from the first element in assuming to be one element array. I read 8 times just to basically train the branch predictor to think, oh, basically he's can go straight because it's in bounds. Then I'll do an outer bounds read. Namely, let's attempt to read at one past it. So let's see what happens. You can see here I train it, so it's all in bounds, and it's all in the cache, so it's warm. Outer bounds read, the first one, is still showing as it basically went past it. Now sometimes you can see if I run it again, sometimes it does 2. Before it realizes, wait a minute, this is actually legitimately change the branch prediction to, oh, it's actually not taken, so I won't read past it. And so, again, this is now how, because it's observable. Now in this case, obviously, it's in the same cache line, and it's a relatively easy case, but in the case of in the Spectre attack, you can do more complicated instructions afterwards, and if you can index indirectly into other memory, you can see what the value is at the point of where it's read.
All right, you're up. Your time is up. Thank you very much.
Any questions?
Came up with a caring picture. I thought it was really fitting for like a security demo, because you look at the website name and then you think, okay, it's a beautiful concept. Caring picture. Okay, so if you look at that, it's very innocuous. There is nothing really complicated there, but it will serve as a way to show what I wanted to show. That is, there is a special code there. It's called lead access of NDPy. So that is the malicious stuff that I'm trying to detect using Circada. So earlier I talked about how Circada can use a rule to detect malicious content, right? So this is a typical Circada configuration I mentioned earlier, and I basically said that just use this rule because I wrote it up, and then it's the awesomest rule that you can write. It's going to be tricky.
Can we hold that?
No, that's fine.
Yeah, carry on. I have to be a microphone stand. Oh, good lord, it's shocking everything here.
Spark.
There is a spark.
We are known for each other for a long time. So this is the rule that I wrote. So if you look at it, it's pretty simple. It says if it has a content called lead access, then trigger this rule. Okay, so it's a very simple rule, nothing complicated. No PCRs, no regexes, nothing complicated. So how do I go and actually trigger this now?
It might be a shocking experience.
So I'm going to just fetch this content of the website using curl. Let me show what's inside. Basically, it does a curl, right? So I can say curl caring picture dot search dot sh. So before that, I want to show where I will be expecting something. That is, I'm going to a log file. You can see that's where Circada logs everything in JSON. And if you don't know about JQ, you should. Who uses JQ here? Okay, the rest of you should learn JQ. Because if you're dealing with JSON every day, if you're not using JQ, you're missing out a lot. Basically, JQ is like awk. You can do queries just using JQ. In fact, yesterday I taught one of my new colleagues to use this, and he's parsing through 300 gigs of compressed log files, then outputting something, within like few minutes instead of writing a program or script to do it. So it's a really useful tool. Okay, so I'm going to just tail this and then watch this. It also does other logging apart from what I'm looking for, but that's fine. So I'm going to say curl, and then we'll go back and see if that is actually caught. It's taking too long. So if you see here, apparently Splunk, which I'm also going to show, is also doing some network calls. So that's why you see logs from Splunk. So this is the actual log that I'm expecting to see. This is an event that was generated that said, oh, this is signature fired, and then what is the alert? Basically, it is possible awesomeness. Wow, that's great. We caught the thing that we were planning to catch, right? So, but this is like very plain JSON stuff. We want more colorful stuff, right? So I talked about SIEMs, SIEMs. So Splunk is one of them. So in Splunk, this is what you do. Basically, you can query, and it's very familiar to people from the Unix background. Feels very much like typing commands in your shell. So I'm essentially saying that just show me all the types of events that are tagged alert. So essentially, that shows me all the alerts that have been caught by Circada, and then they come up in Splunk. But of course, if you know Splunk, you can do a lot of cool stuff with it. You can create dashboards, pie charts. You can track this over time. You can create reports. You can do all kinds of cool stuff. So this is what people usually use to sort of keep an eye on this. To answer Calvin's earlier question, how do you deal with the data that is generated by Circada? So this is how, of course, this is raw data. This is not like dashboarded or anything, but this is where you go to do the polished stuff. Okay.
Thank you very much for answering my question. Excellent.
That is the talk. Thank you.
All right. Let's give everyone a round of applause for doing the lightning talks today.